snowman is going to hand back your quiz. And what you'll do is call your name and then put the quizzes, put them across there. I put the solutions up. Has anybody looked at those things? On one note? Y'all see them? They're up there. And so today, first let me ask this. Are there any questions about any of the stuff we've covered up to this point? To recap, we've done basically Thevenin, Norton, superposition, nodal, mesh, and we've done addition of resistors in series and parallel. So the voltage one. I'll tell you what, why don't you see me after class, all right? On this one, those are transients you're talking. For transient solutions, we've gone through both RC and RL transient solution. There's one thing we didn't cover that's related to inductors and capacitors, and it's the addition of capacitors or inductors in series and parallel. Today I'm going to start there, and then we're going to go into something called steady state behavior of circuits. That's going to be at a constant frequency. So write this down. When you're adding inductors in series, if you have L1 and L2, and then you might as well go dot, 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 Ln, and you want the value of the inductance here, L equivalent. Y'all follow this? You're just adding a whole bunch of inductors, right? Can you all see this?
Yeah.
They're like resistors in series. You just add them all up. There, the equivalent inductance is just going to be the summation of L1 plus L2 plus dot, dot, dot plus Ln. Follow me? So inductors in series are added just like resistors in series to get a single value. How many see this? I want to make sure you do. Y'all went through in this class? Now, if an inductor is in parallel, if you have L1 and L2, and then dot, 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 Ln, so you're going to have Ln inductors in parallel. The only thing you do is treat those as resistors in parallel. The value of L here, the equivalent inductance, will be equal to 1 over L1 plus 1 over L2 plus dot, 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 1 over L to the n. Y'all follow me in this class? I'll do an example. I'm glad I'm not doing it. Yeah.
I'm not really sure about Nortons.
About what?
Nortons.
Okay, let me do this and I'll get back to that. I'll get to some of those questions. I'll go through Norton and Thevenin. Most of that stuff is just look at the lecture, probably brings it up. But anyway, when I have this right here, the best way to do it is with an example. So here's like a question that might come your way. Simple one. Suppose I had 5 Henrys, right? And then I had 10 Henrys, and I had, let's see here. Oh, that's another 10 Henry. And I wanted to know what the value of L was coming into that, the equivalent value. Can you all see this, class? Well, what's it going to be? How do we add these two in parallel? Think of a resistor in parallel. 10 in parallel with 10 is 5, right? 5 in series with 5 is 10. Y'all agree with that, class? That would be 10 Henrys. Y'all with me? Now what happens if I do this? Just work with me on this one. It's a little game, but it'll help me. Now what if I do this? I put another 10 Henrys right there. Now what's the input? Anyone? Well, what is the equivalent inductance of this parallel bunch? It's just 10 divided by 3, right? Isn't that right? 10 divided by 3. Or 3.33333 plus 5, right? So it's really 8.333333 henries. How many series right here? That's how you do it with inductors. I didn't cover it before. Well, what about inductor, or what about capacitors? Are we clear on inductors, class? How many series? Now, I'll give you some problems. Make sure you do the problems. It'll let you establish that thing in your mind. I just took off the thing. Add it. Yeah. Did you have questions? Did I go? Did I go? I didn't erase that, did I? That's it right there. They're just like resistors. Think of it that way. That's it. All right. Where'd you go? Thank you. All right. Now, the next thing we do is capacitors. I'm going to show you an equation that dictates the value of a parallel plate capacitor. That'll help you understand what I'm showing you. Remember, inductor is just a bunch of wire. You string more wire together, it makes sense, the inductance goes up. When you have a capacitor, this is usually a symbol for a capacitor. And that's the capacitance of it. Now, the actual value of the capacitance for a parallel plate capacitor, probably 90% of you know this because you've taken physics and you've had to do these problems. It's proportional to the area of the plates. The plate area would be like meters squared of area, the parallel plates. And it's inversely, that's an area, it's inversely proportional to the distance separating those plates. So the bigger the plate, the bigger the capacitance. The smaller the distance separating them, the bigger the capacitance. The multiplier here on this is really epsilon. And epsilon is called the permittivity or dielectric constant that's in the insulator that separates these two. This is epsilon relative times epsilon naught. And epsilon naught is about 8.854 times 10 to the minus 12 Henry or farads per meter. Epsilon relative's value can be big. It can get up to probably 1,000 to 10,000 for exotic materials. Typical values of epsilon relative is somewhere between 2 and about 20, 2 and 10. All right? But these are just relative things you should keep in mind. Now, a capacitor is an energy storage device. That's fundamentally what it is. You charge it up, it'll discharge. That's it. Now, if you look at this formula and you think about how you add capacitors in parallel, I want you to think about this. I have some C1 here, and I have some C2 here. What happens there? Doesn't it look like really the plates of the capacitor have got more area on them, not the separation distance? How many see that? Assume that they're both identical for now, right? The way you add capacitors in parallel, regardless of how many you have, and you can have this, dot, 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 and this is C of N. These capacitors, the equivalent capacitance here, is just equal to C1 plus C2 plus C3 plus dot, 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 plus C of N. All right? You just add up the values. If you had 2 farads in parallel with 10 farads, in parallel with 10 farads, it would be 22 farads. You add them all up in parallel. It just looks like the area of the plate's getting larger and larger. Think of it that way. Now, if they're in series, capacitors in series, as you might gather, when I take a look at this, the equivalent capacitance there is going to be smaller than the smallest of these capacitors. Here, they look like resistors in parallel, or inductors in parallel. Here, the equivalent capacitance, C equivalent, will be equal to 1 over C1 plus 1 over C2 plus 1 over, and then it goes dot, 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 I should say, 1 over C to the N. You all follow me on that? Now, what's really happening is this. If you think about it, isn't the distance growing between these plates, if you think about it? Think about this. This had a separation of D between these two, right? This has another D. If you think about this, and it's not exact, but it's sort of like increasing the distance between the plates. That's how you add capacitors in series. I want you to know that because some of the problems earlier on asked these things. Most of the time, almost always, you're going to be just given a I'll get you in a second, single inductance value or a single capacitance value. The times that I see it to be important is when you have equipment like you use scopes all the time, right? You've got, mechanical engineers use scopes for all of the stuff and use other measuring equipment. When you have that, the scope has a certain capacitance at the input. That capacitance has to be calculated in any device you connect onto that for a probe. So the probe capacitance with the capacitance of the actual scope have to be added together in parallel. You need to know that or else you're going to make some measurement mistakes for anything that's got high frequency variation. Just keep that in mind. What was your question?
Can you clarify how to add them in series and parallel?
Sure, in series you just add up the values. If this was 10 microfarad, 10 microfarad, 10 microfarad, it's 30 microfarads. If they're in series, it's 1 over C1 plus 1 over C2 plus, you keep going that way. Got it, guys? Everybody? Now there's nothing here that's tricky. You've had this in physics, I think. Didn't y'all have inductors and capacitors in physics? And this basic principle of addition in parallel and series? So that's not a big issue. And I don't focus on that because almost always it's a single element. You don't see 3 or 4 different inductors hanging around and we've got to add them together and figure out a value most of the time. I mean, yeah, on a test you see that, but that's the only place you're going to see it. Now here's what we're going next. And I'll get to the stuff with any questions about specifics with Norton equivalent or Thevenin equivalent or anything else towards the end, but I need to cover this today. So far, we've done DC circuits where we had like 5-volt battery driving from. We've gone through and we've analyzed everything. Then we did transient circuits, only first order transients, where we have charge in either capacitors or currents in the inductor, and we throw a switch. So that's transient behavior. You need to know how to do that for some of the other things you're going to be exposed to. Now we're going into what's called steady state phenomena. Let me make sure you understand this. That wall outlet has a sinusoidal variation of 60 hertz, and it has about 117 volts RMS as its peak. The actual peak value is quite a bit higher than that. That's called the RMS, or root mean squared value. Does everybody understand that frequency 60 hertz does not vary? It is what you call the steady state operator. It is always at that frequency. It never changes. And everything we do is designed, that we can plug things in, is designed around that fact, that voltage and that frequency will be a constant. So how do we go about using that in solving problems? Don't write this down. This is what you don't want to do, but I know it does happen. You don't want to do this. I'll say it again. You don't want to do this. You don't want to say I have plus to minus 120 volts times cosine of, this is really 2 pi times f, but about, it's 120 pi times f times t, volts right here. And then you're going to have a resistor R and say an inductor L. And if you want the voltage here, V of t, the way you would get it, a typical physicist would get it, he would do this. He would assume that I would have a current I of t that would have a cosinusoidal variation, some magnitude, cosine of 120 pi t plus some phase angle, and he would write the differential equation and solve it. Now, I'm not going to do that. That's what you don't do. Did you hear me? You don't solve differential equations. You're going to solve one differential equation, and then everything else will be algebraic, and I'm going to solve it for you. We don't do it that way. And you know what? The voltage here would be I of t times R. The voltage here would be L times di dt, would be equal to this, and we could solve it. Do you all agree with that? We're not going to do it that way. No. What we're going to do is this. We're going to use a couple of things that you know about as engineers. You know about Euler's identity. Now I'll write it down. If you have e to the j omega t, that's equal to cosine of omega t plus j times the sine of omega t. And while I'm at it, omega is 2 pi f. For example, omega is radians per second. Every engineer probably knows this well. Omega is in radians per second. F is in hertz or cycles per second. How many know that the relationship omega is 2 pi f? How many have seen this? If you come through physics, you've seen it, right? If you're a mechanical engineer, you've seen it. If you're a aero engineer, you've seen it. If you've done anything in engineering, you've seen the term frequency used and the relationship between radian frequency that has to do in radians per second and cycles per second or hertz, right? You've all seen this. This is a typical relationship. F is constant, omega is constant. Now, I'm using omega here, and this is called Euler's identity. How many have heard of Euler's identity? There are 3 basic forms of Euler's identity. This is the most fundamental. Another thing is a relationship where we have cosine of omega t is equal to e to the j omega t plus e to the minus j omega t over 2. And we have sine of omega t is equal to e to the j omega t minus e to the minus j omega t over 2j. Here, j is simply equal to the square root of minus 1, if you want a mathematical definition. How many remember seeing these? How many have honestly seen j before, or I, right? Everybody who's taken physics or math at this point has seen this, and you've seen it a lot, actually. If you're in any type, like mechanical, aero, I know you use this stuff all the time, because I know your professors, and I know what they're teaching. Now, when you have these identities, the one we're going to focus on is this one, right here. And I'll show you one thing. We are not going to solve something like this. What we're going to do is say this, that I know that V of m times cosine of omega t is really equal to the real part of V of m times e to the j omega t. Now, if you look at what I've done, if that's e to the j omega t, this is the real part, that is the imaginary part, because its coefficient is j. Do you follow me, class? Everybody understand that? So if I look at this, if I wanted cosine omega t and I had this, it would be the real part of Vm e to the j omega t. Do you follow me? Now, that said, there's something else I'm going to say. And now I'm going to develop it. I'm going to go through the model and show you how this works. I'm going to say one other thing, that the differential equation is not the focus. So you're going to forget about that in a second. I'll show you what the focus is. So, here's some things to know. I'm going to have this circuit. This is this. Remember, anytime I want the actual response of, if I say I have a source voltage Vm e to the j omega t, the observable in my domain part of that is the real part of that. That's the actual showing you the time variation of the source I want. Do you follow me? What we're going to do is use this as the source. So I'm going to apply, it's a complex number now, Vm times e to the j omega t here. That's a voltage, right? I'm going to take that, and I'm going to go ahead and put a resistor, R. Then I'm going to put a capacitor, C. And matter of fact, let me do it this way. I'm going to just put an inductor next, just so I don't make it too complicated. And now, listen to me. This is something that's called this is a steady state response right here. It will give rise to a current, and I can't prove this right here, but I can write the equations and prove it one time with the differential equation, but I'll just tell you this. It's going to give rise to a current that's going to have a magnitude I of m. It'll have a phase angle e to the j theta m, and it will be oscillating at the same frequency. It will be e to the j omega t, whatever omega is. Do you follow? So it's going to have the same periodicity, or rate of change. All right? Now just listen, and you'll get this. That's the source voltage, right? we're going to do voltage drop starting here, and I'm going to go around here. That's my current going this way. So if I come from here to here, I get a voltage increase of Vm e to the j omega t. All right. Now this again is usually what's called a phasor notation, but believe me, I'm going to show you how it reduces the problem's complexity into just algebra. Here I've got a voltage drop. That voltage drop is going to be R times that current, Im, e to the j theta m. That's the angle associated with this magnitude. It's going to be that. And then there's going to be a voltage drop here. That's going to be equal to minus L times the derivative of I with respect to t. I want you to look at this. When I take a derivative of that with respect to t, do you see how the j omega comes out in front? That's the critical thing. So this is going to be really minus j omega L times I of m e to the j theta m times e to the j omega t. Just work with me on this one. My assumption was that I had a source voltage that's really a phasor. It's got a really imaginary part complex right here. And it gave rise to a current that had the same frequency component, but there was a possible phase difference, and there was a magnitude that's unknown. Yes, sir?
When you multiplied your resistance by the current, how come you didn't include e to the j omega t?
Because I missed it. Thank you. You're going to see in 1 second that that goes away. Thank you so much. That was my bad. I apologize for that. Y'all follow me on this one, class? Now, I'm glad you said it. It's going to go away anyway. Do you notice that the e to the j omega t appears in every one of those terms? How many do? Can I not get rid of it? Absolutely. It's not necessary. It's unnecessary, so I can get rid of that. Follow me? Now, when I look at that, if I wanted Im, right, and the phase angle, just take a look at this. If I wanted the current, I could say the current Im was just equal to, this is all equal to 0, by the way. I didn't put that in there. Would be equal to V of m, right, divided by simply R plus j omega L, right? And that would be this number, magnitude e to the j, the phase of that. Y'all see this class? Yes, sir.
What symbol are you using for phase?
For what?
For phase?
This is theta, or, I mean, I could use phi, doesn't matter, it's an angle, right? But here's the better, when I look at this, right here, I want you to notice something. This right here is a complex number, right? It has a magnitude and it has a phase, doesn't it? I mean, just look at this. If Vm is just strict real, that j omega L is imaginary and that's real, right? We have a complex number, right? Please watch this. That means this value right here, this combined value, would be really equal to some magnitude, and I've got it, some magnitude I of m, and there's a phase angle, e to the j theta of m, right there. Now, that's one way of getting it, right? And let me just continue on here. For that right there, y'all realize that the magnitude of I of m is equal to the square root, or is really equal to V of m, right? Over the square root of r squared plus omega L squared. Y'all follow me on this? Magnitude of a complex number is going to be square one part, square the imaginary part, square the real, square the imaginary, take square root. Do you remember this? Give me a show of hands if you do. All right, everybody should have had this. If you have an imaginary number, a real plus j something, the way you get the magnitude is square the real part, square the imaginary part, take the square root. It's just like if you have a right triangle, A this way, B this way. If you want the magnitude, the hypotenuse, you square each side and take the square root. Now, the next thing that happens is the angle. The angle here, well, if you look at this, just for a second, when I take a look at this, the angle of this is just at an angle of 0 degrees, isn't it? I mean, If you have 1, isn't it at 0 degrees implied? You'll follow me on that? It has no angle, it's got 0, right? If it was 1 plus J1, it would have 45 degrees. All right. This has no degrees. What about the bottom one? Well, I have an imaginary over a real. And when you think about, some of you probably haven't done this in a while, if this is the real axis, and this is the imaginary axis, or the J-axis, and what you're talking about is something where you have a real component, and you have an imaginary component, and you have some angle. Well, that angle right there, the tangent of that angle would be the opposite, or the imaginary part, right, over the real part. If you look at this, the angle down here, the imaginary part is j omega L. So this would be actually, would be the inverse tan. The angle would be tan minus 1 of omega L over R. Please look at this. Think about this, right here, pardon me. Omega L is imaginary, right? That's vertical axis, right? R is horizontal. The angle would be the inverse tangent of omega L over R. Can everybody see it based on that diagram right there? Show of hands here, how many can? It's very easy, it's very, very common stuff that you've done before. It's a simple right triangle. The real axis is horizontal, the imaginary is vertical, all right? Now, when you have this angle downstairs, what happens if I take it to the top? Class? If you have 1 at 30 degrees in the denominator and it comes to the numerator, it becomes 1 at an angle of minus 30. You all remember this? Sure. If you take an angle from the denominator to the numerator, you flip the sign. So this is going to be simply, the angle of this is going to be 0 degrees plus this angle, or it's just going to be equal to, the angle will be minus the tangent minus 1, the inverse tan of omega L over R. And that's the angle associated with this. Which means now I can get the magnitude and the angle associated with IM. Do you all follow me? Now I want you to hear me carefully. I started with this, but really my source was actually the real part of V of M e to the j omega t. That was V of M cosine of omega t. Do you follow me? When I take the real part of this, I get that. Now, if I take the real part of the current, all right, the real part of the current, and I'm going to have to include, remember I erased e to the j omega t, then I'll get the actual current. Please just watch this. Some of you will feel uncomfortable with this for a little bit, but watch this. I'm going to assume for a second that I have a current I equal to 10 e to the j 30 degrees, right, amps. There's no j omega in there. That's an angle and a magnitude. Follow me? I'm just assuming this to help you see. Now suppose I wanted the actual time domain form of this. What is really there that's measurable? The way you get it is this. I of t would be equal to the real part of I. Sometimes they put a little tilde on there. It means phasor. Times e to the j omega t. The reason you put the e to the j omega t in there is I suppressed it. Remember when I erased it because it appeared everywhere? Now I reintroduce it and I say if I take that times I and I take the real part, I get the actual I of t. Well, there's the phasor form, right? When I go ahead, I'm going to say my I of t here will be equal to the real part of 10. I've assumed that. And it's going to be e to the j, and then it's going to be omega t plus 30 degrees. I did this on purpose. Now, what will the real part of this be? What's the real part of 10? No tricks. 10, right? There's no j in there. Follow me? It's everything. 10. What's the real part of this part of the equation right here? Well, can't I expand e to the j omega t in terms of plus the phase angle in terms of Euler's, right? And I have cosine of omega t plus 30 degrees plus j sine of omega t plus 30 degrees. How many understand that? Absolutely, that's the reason I put Euler's down. So this becomes I of t is just equal to 10 times cosine of omega t plus 30 degrees. I did this on purpose. That would be the observable current. That's in real time. This current up here, magnitude and phase, that's not observable, but you see how you just turn this thing into a cosine omega t and add the phase angle? How many see this, class? Now this is observable. Here, we can solve these equations without solving a differential equation using the standard tricks that you have, Laplace transforms or anything like this. We circumvent it, and now it gets really easy in a second. But I gotta say one other thing, heed my warning here. You see this right here? Circle that and say something wrong. Here's why you don't put 30 degrees in here. Almost without exception, omega t has the units of radians. Follow me? This is the units of degrees. You always take that and turn it into radians. Now 30 degrees is what? It's pi over 6 radians, isn't it, class? Isn't that right? Sure, so you put pi over 6 here. I put degrees down there because you're going to do this on a quiz and mess it up. So it's pi, I hope you don't do it on a quiz. Let me not try to be prophetic about doing it. I want you not to do that on a quiz. What I want you to do is recognize everything is in radians, usually when we get the time domain values, omega t plus that. Now, if you want to work in degrees and your calculator is working degrees and everything's in degrees, fine. All right, but remember what I tell you. Got to make sure, because omega is almost always radians per second. That's the reason I'm cautioning you. All right, so now that I said all this, let me show you the tricks involved with solving circuits without solving circuits, using differential equations. And start this on a new page if you don't mind. This is important. This stuff's in his book, but it's not. I want more emphasis on this stuff. Actually, I'm not sure how much of this is in his book. I don't know if he puts Euler's equations down or not. So now I'm going to show you something you'll like that makes your life a lot simpler than it would be if you were taking this course probably for graduate physics course or something like this. So put this time domain here, and then put phasor or frequency domain. I like phasor domain because that's what we talk about, magnitude domain. Now, over here, when we have a resistor, R, and it has a voltage across it, plus to minus V of t, and a current going into the positive terminal, the relationships are V of t is equal to I of t times R. This shows you how the voltage is going to be measured. Positive current flowing this way creates a plus to minus voltage that's equal to R times I of t. You can also say that R is equal to V of t divided by I of t. Voltage over resistance, over current is resistance, right? That is for a resistor in the time domain. In the phasor domain, it's the same thing. R is equal to V phasor over I phasor. Nothing's changed. Got it, everyone? Now next, time, and then phasor or frequency domain, right here. Now we talk about an inductor. For an inductor, we have I of t here, we have V of t here across the inductor. But V of t, the voltage across an inductor, is L times di of t dt. All right, that's a differential relationship, isn't it? The derivative is what's important here. In the phasor domain, what you get is, matter of fact, let me do it this way. Well, I'll just leave it like that. Then a phasor domain is V of, and really V phasor is equal to J omega L I phasor. And really, write this down, the impedance Z of an inductor. Symbol Z means impedance. This is like AC resistance of an inductor is simply equal to J omega L, and that's the ratio of V phasor over I phasor. Now this is very important. It's saying I can replace an inductor in a circuit that has a steady state drive, either cosine or sinusoidal varying voltage or current of a constant frequency with just j omega L. Now omega is 2 pi times the frequency of operation. I'll do problems so this really gets beaten home to you, all right? So this is important. This is like the DC resistance that we've dealt with, all right? It's a ratio of voltage to current. Finally, we'll talk about time and phasor. When we have a capacitor, we had a current I of t here give rise to a voltage V of t here, right? But we found out that I of t was equal to C times dV dt. That was the differential relationship between current and voltage in the time domain for any kind of transient behavior, right? We just did this. In the phasor domain, it's really nice. In the phasor domain, the relationship from V phasor to I phasor for a capacitor is just 1 over j omega C. And that is like an AC resistance. By the way, what is 1 over j, anyone? Well, isn't j really 1 at an angle of 90 degrees? How many know that? Right? 1 at an angle of 90 degrees. 1 over j is 1 at an angle of minus 90 degrees or minus j. So this can be rendered as, and you can call this the Z of the capacitor, impedance of the capacitor. You can just say Z of the capacitor, if you want to, is minus j over omega C. It's not critical. Now, I'm going to tell you this. Most of the time, when you're beginning AC problems, they will specify the impedance of the capacitor or inductor is either like J 50 ohms or minus J 50 ohms, something like that. And you don't have to do the omega times L or omega times C most of the time, not all the time. Follow me? I want to do some simple problems to help you see this. And then I'll show you all the way how to get back to the time domain with the final answer. Because you're going to apply what you've learned earlier with all the different circuit analysis tricks to now circuits with capacitors and inductors. So, work with me on this stuff. And I'll give some homework. I'm going to use some problems out of this book. I may use a couple different books, but I'll give you the solution. Let me just take this. Oh, one other thing. You add impedances just like you add resistances. Following? So I guess that's a good place to start. We're going to find out what the impedance is of this. This is actually pretty good. Let me do a couple of these things before I get into the circuit analysis. This is 4-6 in the homework I'm going to give. It says, what is the actual impedance Z for this circuit where I have 60 ohms and I have L equals 0.2 Henries, and it is at omega is equal to 377 radians per second. We'll do this one. We'll do a couple of, this is going to be an easy one. Now, I'm going to tell you, this gives us a frequency, right? That's 2 pi times 60 hertz actually. It's 120 pi, 377, roughly. So if we look at this and we want to know what to replace that with, that would be replaced with J omega L, or J 377 times 0.2. Can anybody give me that value? Got a calculator?
That's 75.4.
All right, so that's going to be equal to J 75.4, and the units are ohms for impedance. That's right here. Are these two in parallel, class? How many say they're in parallel?
Yeah, they don't use parallel.
Parallel. They're in parallel because they have the same voltage across them. If you put a voltage here, it must be developed here and here, right? They're the same exact voltage. It's like electrical pressure. Now, if you take a look at this, what would the value be of Z? Well, if they're in parallel, and there's only two of them, I could take this times that over that plus that. Do you agree? Or I could take 1 over that stuff, right? Either one will get me where I'm going. I'm going to multiply this, 60, you can do this with me, times really J 75, 75.4 over 60 plus J 75.4. And again, I'm just treating these as I would resistors. You do it exactly like that. Are you with me, class? Now, look at this. What do you get for this? You see, I'm going to get what? I'm going to get a complex number, correct? I could have a real and an imaginary component of that, or I could have a magnitude at an angle, couldn't I, class? Can somebody give me this in terms of a real and an imaginary part? Anybody that has a calculator? You have a calculator, don't you? Do you mind doing this for me? I'm trying to make this as easy to understand as possible. I'm showing you what's called just AC resistance, called impedance of these elements. And that way we're doing circuits problems that we've been taught to, not writing differential equations, loops and loops of them, and solving them simultaneously. That takes a long time. Anyone? Remember, J in yours may be I in your calculators, small I. I mean, you've done this stuff, surely, haven't you? Yeah.
Oh, we got written there next to J 75.4.
Ohms. The units are the same as resistance. They're ohms, or we couldn't have them. Anybody? Tell me when you
My
get.
calculator gave me a number that plus something. I've never seen it give me this notation.
Could
Give
you-
me 36.73
Hold it,
plus
36.73
7, and then I give you one more.
plus J7.
No, then it says plus 29, and then a dot and a semicolon. Oh, there it is, plus 29.2 I.
Yeah, that's J. So it's plus J 29.2. And this is ohms. Now, I want to tell you this. Your calculators will use I, not J. In electrical engineering, we do not use I for imaginary numbers because I is representing current all the time. So we use the next best thing, J. That's just telling you the way it is. We don't use I in math, they use I. All right, I don't know what they use in physics, but we use J for imaginary numbers. Now that's a complex number. You can also, don't clear your memory, because you can go to polar on your calculators usually with 2 punches of the button. If you want to go from rectangular to polar, it's usually just a function key and a stab. It'll give a magnitude and angle. Can you give that to me? It's going to be somewhere in the neighborhood of about 45, I think, at an angle of, what is it?
46.95 angle, 38.5.
At an angle of, say that again?
38.5.
All right, that's the equivalent impedance of that. Now for any other, if it was a capacitor we could do it, we'd only use the impedance of the capacitor as 1 over J omega C. Follow me? For any other sequence of resistors, capacitors, inductors, you will treat them all as they are resistors, only instead of the inductor value or capacitor value, you will replace them with the impedance of the capacitor inductor and then treat them as complex numbers. That's the way you do these problems. Now, another one we're going to do, and I want to make sure you see this because there usually are a few questions that are unsaid because you're not quite sure how to state them. Here's the next one. That's 2 ohms.
Yeah.
2 ohms. minus J2 ohms, and then J2 ohms, and what I want is the impedance here between A and B. So I want the AC resistance there. Now just take a look at this, because you're going to get this. You all see these two are in series. You agree with me? So the impedance of this leg right here is just 2 minus J2. Are you with me? Now, y'all see that this J2 here is in parallel with those two. How many see that? And you see that the parallel combination of these two plus 2 would be the total impedance. Do you agree? How many agree with me there? All right, so what is the equation for this going to be? Well, here, I'm going to start by saying Zn, or ZAB, would be equal to 2. That's that. Then I'm going to add the parallel combination of those two. And the way I'm going to do it is this. I'm going to take this times this over this plus this. Do you follow me? You're going to see it's going to make it real easy in a second. So I'm going to say plus, and then it's going to be J2 times 2 minus J2 over the sum 2 minus J2 plus J2. Y'all agree with that? Please make sure you see what I've done. Clear on this one, everyone? In the far back there, can you guys see? Far back? Okay. What's this going to be? Just to make sure. Can everybody see I have 2 minus J2 plus J2? What is minus J2 plus J2? 0. Zilch. So isn't that just 2 left down there? Agreed? Now, keep watching. What is 2 into 2? 1. So now I get rid of this one, right? Agreed? Work with me here. What is J times 2? 2J. Right? 2J. And what is J times J? Well, square root of minus 1 times square root of minus 1 is minus 1, right? With the minus in front of there is plus 1. So my ZAB is actually 2 plus 2 plus J2, or it's simply 4 plus J2. You all see that? How many see that right there? It is as straightforward as it looks. Yes, sir.
Did you go over how you got rid of the second J term?
Well, what I did was, in the denominator, remember I had to add all these terms, right? Right?
Yeah.
All right, that's plus J2 minus J2 is 0, isn't it? Plus 2. And then I took that plus 2, that's what's left over, and divided it into the J2 on top, which is just J. Are you with me, class? If you look at the video on this, it's going to be crystal clear. Now that's how you add, I'm showing you how to add things using complex number notation. The minus J anything is always a capacitor, the plus J anything is always an inductor. Keep that in mind. Now, after that, I got a minute for you. I know you guys are anxious. I'm going to tell you that this stuff kind of falls apart the way I'm showing you how to do it. You're going to thank me if you get into a job interview sometime. I always wonder with these interviews that I talk to people and they're trying to weed out anybody that doesn't really get it. So they ask them questions they should know the answer to, but it's the way they go about getting the answer that tells them. For instance, if a kid starts writing differential equations, if they got a constant frequency, say a cosine 377t source in an RLC circuit. If he starts writing diffie Q's for that, he's like, he's not going to be here long. That's not the way they're taught to do it. In physics, they do that maybe, but in engineering, if you come through that, you're always after the answer, an accurate assessment of the answer with a minimal amount of work. Yes? This is J times 2, that's minus J times 2. Give me a second, guys. Don't blow off yet. Now, being nice, I can be not nice. What I'm going to tell you is this. I'm going to give you about 5 problems tonight related to this. I want you to do them for next time. I know a lot of people blow it up. The reason I'm telling you this is because next time it's going to get, we're going to take, and we're going to jump right into some more difficult material. I need everybody to do this to make sure you're up to speed. Don't not do this. Because you will start to get behind in ways you've never dreamed.